Okay, I guess we can probably start. First of all, I mean, I'd like to do a little bit of introduction to this FOCETA seminar. So today's seminar will be presented by Brian, who will give a talk about the exact robustness verification for attention network. So Brian, I'm now offering to you.
Okay, yes, thank you very much, Professor Shelley, once again. Yeah, hello everyone, welcome to the seminar today. This FOCETA seminar series on trustworthy autonomy, and today specifically I'll be talking about exact robustness verification for attention networks. And to be specific, this is a work done for within the scope of work package 3 in FOCETA, which is under the name of verification and validation for autonomy. And yes, again, I'm Brian from DENSO, Germany. And together with me in this work, we have Dr. Chih-Hong at Fraunhofer ICAS, Dr. Maximilian Kneissl at DENSO too, and my PhD supervisor, Professor Knoll at TUM. Okay, so without further ado, this is a short outline for today's seminar. And briefly, there are mainly three main parts in this seminar. First, I'll give a more general introduction into the problem of neural network robustness and the verification of neural network robustness. And then I'll dive deeper into the main topic of today's seminar, the work that we've just concluded recently on exact robustness verification for attention networks, why we want to target at attention networks, and what methodologies and techniques we've applied in the studies, and of course some experimental results. And finally, I'll conclude with the summary and limitations as well as future direction in this regard. So yeah, without further ado, neural network robustness and its verification. So nowadays we've seen abundant neural networks in lots of applications, real-world applications. For example, we have autonomous driving on road automated vehicles, where the perception modules, or even nowadays end-to-end planning or controlling modules in the autonomous vehicles are now based on neural networks. Or we've also seen aircraft autopilot applications too. And not to mention that we also have medical diagnosis systems or even surgical robots nowadays in the hospital, which are based on machine learning models or even neural networks models. But now then the problem, the serious problem, is that whether we can really trust them or not. And studies have shown that this is probably a question mark, because for example, on the left, we are seeing a misdetection of a stop sign under an illumination alternation. So especially we can, as humans, we can see the traffic sign in this image quite simply as a stop sign, but somehow under this minor illumination issue, the computer or the automated vehicle now tells us this is a speed limit at 30 kph. And on the right, we have other examples from the medical domain. So here we have misdiagnoses under image or text manipulations. So for example, on the upper part, we're seeing an adversarial rotation, where so after which the computer can no longer withhold the original diagnosis. So saying that the patient is actually now malignant instead of being in a normal condition. And in the lower half, we see two text substitutions, namely from back pain to lumbago, and alcohol abuse to alcohol dependence. And somehow under this perturbation or under this manipulation, the computer predicts the patient's opioid abuse the risk of opioid abuse from high to low now. So yeah, these are real world evidence showing that neural networks cannot really withhold their performance correctly under some minor or virtually equivalent input changes. And perhaps this tells us something, or we cannot trust them fully. Now, maybe we say at least not before verification. So what does that mean? So here we, on the bottom right corner, we see a common process for neural network designing and deploying for general applications. Literally, we have data collection and data processing, after which we usually train the model, and at some stage, after some satisfying performance, we deploy the neural network model into its real-world application, right? But for mission-critical applications, we want some evaluated performance more than just some empirical numbers. So literally, we want to know whether or not the neural network model is behaving or performing on top of some certain properties. So, for example, for robustness, we can put the neural network model after the training phase into some verifier, and the verifier can now tell us if there are some counterexamples, and thus the neural network model is no longer robust. And after which we can feed the counterexamples back to the data processing stage, the model training stage, and the verifier stage once again to iteratively assure that the neural network model is eventually robust. And until then, can we deploy the neural network model into runtime real-world applications? So yeah, this is the general idea of model verification sitting in between the pipeline, the common pipeline of neural network designing and deploying. So as said, robustness is just one of the various properties that could be verified against. And so once again, robustness refers to the phenomenon where a neural network could misdetect or mispredict nominal input into some bizarre behavior, into some bizarre output in the case of certain input perturbation. And we can also verify model properties against fairness, with regard to fairness. For example, if a company wants to decide if a candidate gets an interview or not, then it has to make sure that either it doesn't bias against a Mr. or a Miss in this process. And similarly, we can also verify the monotonicity of a function. So, for example, a bank would always want to base the amount of loan monotonically on the amount of income a candidate has. Or likewise, we also can verify the interpretability of a model, where we want to really know for what reason a neural network model is making its decisions. So yeah, there could be many properties one would have to verify before model deployment. The list can go on and on, as long as the property for verification can be specified and mathematically formulated down. Right. And today we'll just focus on this robustness property, which is probably arguably the most relevant property in autonomous driving, safety, and trustworthiness. So yeah, for the problem of neural network robustness, what we have seen is such a phenomenon where again, the neural network cannot withhold its prediction under some minor changes at the input. And let's now take a deeper look into the mechanism behind this phenomenon. So essentially, each of these images can be represented as one point at the input space, where we have nominal image located at the center here in the diagram, and the perturbed image sitting around within a neighborhood. And technically, we call this neighborhood the admissible perturbation region. And I will explain in one moment why there is a norm of admissible here. But for now, let's assume this there is this admissible perturbation region, and we'll pass this region or this set of input essentially through the neural network. And if this is if this is right, let's assume a non-robust neural network for now. And at the output space, we'll essentially get also a region being mapped from the admissible perturbation region at the input space. And technically, we call this the 𝐒𝐧𝐥𝐢𝐧𝐸 adversarial polytope. And now the problem of neural network robustness stems from the fact that this non-robust neural network can actually, or its decision boundary cuts through the 𝐒𝐧𝐥𝐢𝐧𝐸 adversarial polytope as shown here. So essentially, it excludes the data point, the perturbed data point outside of its decision plan for the correct set. Right, and now if we want to mathematically write down this phenomena, we can basically do as follows. So we have a nominal data point x belonging to the input space, and we also nominate some perturbed data point belonging to the epsilon bounded norm ball, which is the admissible perturbation region of the x, of the nominal input x. And we pass them through respectively through the neural network, and ended up with the predictions f of x and f of x of prime. And now we regulate that f of x equals the ground truth label of x, which is in this case, for example, the stop sign, and f of x prime does not equal the ground truth label of x, where we see the 30 kph speed limit and the ground truth stop sign. So yeah, we can now quite easily imagine that in the case of a robust neural network, it could effectively, or its decision boundary could effectively contain the entire 𝐒𝐧𝐥𝐢𝐧𝐸 adversarial polytope, and thus having all possible points here within this region classified as the correct prediction as the ground truth label. Okay, so having seen that phenomenon, or having formulated that phenomenon, let's try to formulate the verification problem on neural network robustness. So again, we have this nominal input, and it's of a admissible perturbation region, and also the 𝐒𝐧𝐥𝐢𝐧𝐸 adversarial polytope at the opposite face, and neural network decision boundary here. And we want to denote here an 𝐒𝐧 verification perspective, meaning that we not only want to know whether or not the neural network is robust with respect to this data point, but we also want to know how robust this neural network is on top of this data point. So essentially, we ask the question, to what extent we need to perturb this nominal input such that the neural network no longer withhold its prediction. And essentially, it can be depicted as this diagram. So we nominate some other input, some perturbed input, such that the neural network can no longer withhold its prediction. And effectively, this can be formulated into a optimization problem. So we want to find the nearest counter example which is called technically the minimum adversarial distortion within an admissible perturbation region here, and satisfying the misprediction constraint. Right, so this is the overall background or the basic formulation of neural network robustness verification. And sometimes reasoning on top of that exact adversarial polytope is really difficult because, as we can see, it is non-convex. And to circumvent that non-convexity, some studies will argue or reason the behavior of this neural network with some outer approximation of the exact adversarial polytope using some convex shapes, and which we'll see in one moment how they do that. But the idea here is to relax the neural network's behavior such that the computation can be easier. And now, as said, the verification problem is certainly non-trivial, and the fundamental challenge here lies in the activation layers in between the linear transformation layers of neural networks, where we usually nominate the redo activation unit as one activation function within the neural network. So graphically, we can depict the behavior of a redo unit as such, where below 0, if the input is below 0, then the output is 0. And if the input is above 0, then there is a linear behavior. And to solve this behavior, or to reason this behavior, there are essentially two approaches. One is, as said, as shown in the previous slide, linear relaxation or convex relaxation of such nonlinear behavior. So one could bound the behavior of this redo unit with two linear lines and approximate the neural network output with these two linear functions. Or for exact reasoning or complete verification, we would need exact encoding. So, for example, mixed integer programming is a solution for that, where we nominate some integer variable a, in that we differentiate the behavior of this redo function in a non-activating region and an activating region, represented by 0 or 1 of the integer value here. So if a is 0, then the upper two equation will be activated, essentially representing the left part of this redo activation. And if a equals 1, then the lower two equations will be activated, essentially representing the activating part of the redo function. So with such we can basically encode the behavior of neural network into the optimization problem and solve the optimization problem accordingly. But the problem here again is that there is so many neurons and so many nonlinearity in the neural network, and we will have to somehow tighten the bound of these the behavior of the neural network or the activation unit, such that we can solve the optimization problem effectively. So yeah, again, these are really non-complex constraints, and thus rendering the optimization problem NP-complete, meaning that the worst case performance of these algorithms would be exponential, of exponential time. And furthermore, we have large networks coming into reality, and also different kinds of activation function as seen in the attention networks, for example, the transformer, which I'll be given more details on later. So yeah, again, large networks and various activation functions further worsen the difficulty of this verification problem. Now, the state of the art, just to mention, is that for incomplete or approximate methods, we can deal with some neural networks of the size of 1 million neurons, up to 1 million neurons nowadays, and for image classification tests. And for exact encoding methods, we can deal with up to 100,000 neurons, also in the region of image classification. And for attention networks, such as transformers, we can have neural networks of up to 10,000 neurons being verified in the realm of natural language processing. And we are seeing a lack of exact verification methods for attention networks. And we believe that a network of size 1,000 neurons should be verifiable according to this order of magnitude. Right. So that brings me to the work that we've done on exact robustness verification. And I'll give now first a motivation on why we target the study on attention neural networks beyond the reason the lacking of the verification methods for them, as shown just now. So over these years, within probably the last couple of years, we've seen lots of studies, lots of academic researches showing that attention mechanism, again, which I'll be giving more details in, attention mechanism have shown superior performance against general conventional neural networks in lots of applications, from natural language processing to object recognition. And beyond academic areas, we also see industrial applications, or even companies such as Tesla or Cruise, which is a company supported by General Motors and Honda, using attention mechanisms in their perception pipeline, and also I believe also control and planning modules too. And yeah, we are really seeing this big trend of attention mechanisms in both academic and industrial applications. And now this really prompts us to study to examine whether they are safe enough to be deployed on road in real world. And let me, as I promised, let me just give a more detailed introduction into this attention networks, what we call attention networks. Essentially, they are neural networks that are based on attention mechanisms, as shown here in the example of an image classification test. So essentially, we have an image divided into patches, and these patches will be flattened into vectors. So, for example, this image will be transformed into 9 vectors, and each of these vectors together will be passed through this neural network, this attention network, within which we have nominal layer normalization, and also most importantly the multi-head self-attention mechanism, and within which we have the query, the key and value pairs. So essentially this mimics the process of data or information retrieval in information theory, right? So we query each patch with other patches and find the attention, or find the most important regions in one image against each other, and output the enhanced version of the vectors at the output space. And this process goes on and on iteratively for L times, and at the output space we can classify the image with as its label. And genuinely, we see some really effective low-level latent space filters, as shown in the study. Here we see low latent phase filters that could be effectively produced as convolutional neural networks as before. And at a higher level, at the image space, we also see really effective attention mechanism or attention maps being shown on the input images as shown here. So yeah, now the question is, beyond this, we want, beyond such empirically shown performance, we want to know the robustness of these kinds of neural networks. And then, so that's the reason we put them under verification. But before that, we have to quickly find out that there's some problem or some obstacle blocking us from verifying them exactly as formulated as before in the introduction part. So essentially, there's this softmax. Again, this is a nonlinear activation function sitting in between the linear transformation layers, which render the neural network's behavior nonlinear and non-convex anymore. And this essentially is the bottleneck of the verification problem. And so just to illustrate, the softmax function is based on the exponential function or the exponential normalization of one value within a vector over the other elements of the vectors, right? And eventually producing a 0 to 1 probabilistic distribution. And yeah, as I said, this is the bottleneck of the verification problem. And the technique or the tactic that we took against this bottleneck is to find a linear approximation or approximation of this softmax function that doesn't require or doesn't exhibit this nonlinear behavior. And that, or fortunately, we find this sparse max activation function being proposed by Martins and his colleagues, where I'm not going through details into these equations, so I'm just showing that essentially the evaluation step or the computation of this sparse max, this approximation towards softmax, only involve sorting or max or the argmax or quadratic function in between. So essentially, the ultimate result of this approximation is such the piecewise linear approximation of the softmax activation. And with such substitution, we can finally regulate the neural network's behavior into this optimization problem. Right, and that's how we deal with this nonlinearity problem. And beyond that, we also see another bottleneck in the layer normalization layers. So essentially, originally, to compute the layer normalization, we have to compute the variance, so the mean and the variance of an input vector, where the variance is defined based on a quadratic function. And again, encoding a quadratic function into the mixed integer optimization problem will render the optimization really hard to solve. And our solution to that is to simply take out the variance part from this layer normalization, so as to trivialize the operation of this neural network. And of course, one would argue that after such trivializations of neural networks, the neural network could probably behave not as good as before as using the more complex operations, so namely softmax or this quadratic layer normalization. And I will show in one moment a comparison study on accuracy after such substitutions. But for now, I just want to emphasize that with such substitutions or trivialization of the neural network, we can finally formalize these attention neural networks into an optimization problem, or more specifically, mixed integer quadratically constrained programming problem, where we are given a neural network f of x, and the input x with the epsilon bounded normal, the admissible perturbation region, and the ground truth label, and we want to minimize the perturbation that would alter the neural network's prediction within such region. Okay, so now again, as shown in the introduction part, solving this mixed integer programming problem is unfortunately still very difficult in that the solver, so for example, in our study we use Gurobi. These kinds of off-the-shelf solvers, we has no idea of the general architecture of the neural networks. It's only getting a bunch of constraints and an objective function and tries to give an answer on that objective. So what we would try to do is to give as best as possible we can to this optimizer so as to aid the solving of the optimization problem. And here I will just give two examples of heuristics that we have applied in our study, but they are much more in the literature and also in our paper. But generally, we find that the two that I'm going to share here works the best. So the first is interval analysis. And in our paper, we have found a novel technique to bound sparse max or generally softmax activations. So again, given an input vector, the sparse max or softmax activation output a vector within 0 to 1. So for example, a vector of 7.2, 6.8, and 10.3 will eventually end up as 0.04, 0.03, and 0.93 under sparse max activation. And now the task is to propagate the bounds for the input through the sparse max activation and to the output space. And so we want to know the bounds at the output for this activated values. And for example, if we have these values respectively for the upper bound and the lower bound here, we want to calculate the upper bound of A1 here. And effectively, we find that to calculate the upper bound of A1, essentially we can take the upper bound of U1 here and the lower bounds of U2 and U3 here, as shown here. And as such, that we know that the upper bound is 0.2 for A1. And similarly, for the lower bound, we take the lower bound of the input of this neuron and the upper bound of the input of the other neurons, and finally arriving at 0.03003 in this case, and so on and so forth. So we can do that similarly for the second neuron, taking its upper bound and the lower bound of other neurons for its upper bound calculation. And then we eventually arrive at a much tighter bounds or intervals as compared to a naive bound 0 and 1 for a probability function. And I will show in one moment empirically this bounding technique benefits us for acceleration of around an order of magnitude. But before that, I would just like to share that the second effective technique in this regard is region partitioning. So recall that we have the admissible perturbation region in the beginning of the input space for verification. And what we can do effectively is to divide or partition this region into sub-regions. And we can verify the neural network on top of this sub-regions one after the other. In that if we do not find a counterexample in this smaller region, then we can go on into this larger region, and so on and so forth. And such reduction in the region area or volume will help. It will also help a lot in the verification seed. All right. So with that, I will now share our experimental results. So we tried not only strive in terms of neural networks variation, but we also try to go beyond image classification tasks and natural language processing tasks. So here we experiment or evaluate our techniques on industrial applications, namely lane departure warning. So it works as follows. So, we collect our data from the high-D data set, which is essentially drone-based recordings on German highways. And we process these data into feature vectors where we have, for example, lane existence or distance to lane center, or longitudinal velocity and time to collision of surrounding cars. And we feed these features into different kinds of neural networks, namely multi-layer perceptron, which is piecewise linear neural networks, and attention networks, which was introduced just now. And we want them predict the direction and time to lane departure based on the extracted features. And finally, after some stages of training, we feed the trained or static neural networks into the verifier and find the robustness values respectively as defined in the introduction. Okay, so now as process, here's the ablation studies on the heuristics that we've applied. So we see that after the naive encoding, the time for verifying one data point is roughly 2,000 seconds, or almost growing up to 1 hour. And after the application of our proposed heuristics, this number drastically reduced to 200 seconds, which is roughly 3 minutes for one data instance. So we effectively see a speed up of over an order of magnitude with the proposed techniques. And also, before diving in the robustness benchmark, I just want to show that in terms of accuracy, after substituting the activation layer and the layer normalization operation, we see that replacing softmax with sparsemax actually does not degrade accuracy performance. And in fact, it boosts the accuracy a bit. And just as a conjecture, we suspect that this improvement in accuracy sort of is a analogy to the effect of replacing sigmoid functions with redo functions in piecewise linear neural networks. And okay, so beyond that, we also see similarly applying different layer normalization hardly affects accuracy, as shown here in different colors for each types of neural networks. And last but not least, changing the architecture from attention networks to piecewise linear multi-layer perception does have a retrofit effect on accuracy. So now let's take a look at the robustness performance of these two respective neural networks. So here is the result, the diagram showing the result of different data points that we've verified on for multi-layer perception on the vertical axis and attention network on the horizontal axis. So here in the middle, the dashed line represents a place where the two kinds of neural networks perform equivalently. And so now the data points on the right will represent places where the attention network has higher robustness. And the left part will represent the place where the multi-layer perception has better robustness. And what we see in this diagram is that data points are rather equally distributed over the upper or the left and the right triangles. And also there is a large cluster on the upper left corner here, showing that multi-layer perception is much more robust than attention neural networks for this many data points. And generally, we can sort of conclude that attention network is not necessarily more robust than its counterpart. And we see this as a opposed finding to related empirical work on vision tasks. So that brings me finally to some concluding remarks. First, robustness. I hope I have convinced you that the robustness is a critical issue of neural networks, for which real-world system failures have been shown empirically or theoretically. And as an even illustrative example, here we see a segmentation work or task where we want to classify every pixel in one image into its specific class. And on the upper row, we see a nominal case. And on the bottom row, we don't see any perceivable perturbation on the bottom left figure here, but somehow there is some perturbation around the Mercedes-Benz logo here, and it renders the segmentation neural network outputting some very nasty output as shown here. And so we argue that robustness verification is one, it's not the only remedy for the issue. And we conduct the first study on exact robustness verification for a specific kind of attention networks. We trivialize the neural network with linearized optimization, linearized operations, and ending up with a mixed integer quadratically constrained programming problem, and further proposing acceleration heuristics, and show that although attention networks tend to give better accuracy, they are not necessarily more robust to their counterparts. So perhaps as a takeaway message, we conclude that it is necessary to evaluate and verify both neural network accuracy and robustness performance in all different sorts of tasks before deployment. All right. Okay. So just as a add-on, the limitations and feature directions for this neural network robustness verification studies. So what we've seen so far in the discussion and our study is that these studies are still fairly constrained within design time verification, and meaning that the neural network is trained and put statically into the verifier. And we want to move beyond this design time domain into the runtime verification or monitoring pipeline. And for example, we can do that with different sensor modalities, because what we've seen just now is we generally need ground truth label for these verification works. And what we can do is to feed some feedback or signals from other sensor modalities as ground truths or as comparison for verification on vision tests. And also what we've seen is point-wise analysis, and how we can go from this kind of analysis to ODD, operational design domain complete assurance, is what we would like to strive towards. And as an example, we've seen this image in the beginning, and this is just a nominal case during evening, and during under a clear weather condition, as depicted here as in this box. So what we can do is combine point-wise verification analysis with combinatorial testing in order to cover the more aspects of the entire operational design domain. And also, once again, we are still very limited to small networks and simple tests. And we would like to try with perhaps probabilistic verification in order to verify real-world applications and real-world network sizes. But as a conclusion, as a prompt, we would like to foster more discussions and R&D efforts with our studies in this regard. And with that, I will conclude my presentation today, and I thank you very much for your attention. And I very look forward to your questions or remarks. Thank you very much.
Thank you for Brian's presentation. So I think we still have time to take in a few questions if you have. So probably I can start. So when you are doing the piecewise linear approximation of the I think it's softmax. So are you doing this during the training, or you actually doing this during the verification?
Yes, so actually we did it. We essentially replaced softmax with sparse-max for this attention networks, and we did training for with sparse-max directly, and that's why that's how we came up with the accuracy benchmark.
Okay.
As shown here. So we have the sparse attention and soft attention as general studies use. And,
okay, so in the end, the network is basically a piecewise linear network, right? Because I mean, softmax looks like the only element which it leads to continuous.
Yes, piecewise linear on the activation here, but more precisely quadratically behaving as a neural network as a whole, because of this attention mechanism comparing using dot products between the query and key values. So we have this matrix multiplication in between still that renders the neural network a quadratic function eventually. And that's why we need the quadratically constrained programming optimization problem in the end.
Okay.
Yes.
Any other questions from the audience? Okay, the next question. So you seem to get a different conclusions with what the other papers talk about in terms of the robustness of the attention network.
Yes.
Do you have any insight of why you get completely opposite conclusions?
Yes. So this is a very critical question indeed. Unfortunately, we don't have probably a good answer for this, but what we speculate is that networks, they generally extract different features for different tasks, meaning that they have different focuses on different parts of input for different tasks. And for us, we are performing lane departure warning test, which is essentially a time series classification and regression test, because we want to just predict the direction of lane change and the time to lane change, which so essentially a classification and a time feature vector-based classification and regression tests. And what we have nominate here are tasks on vision, so image classification tests. And so for these kinds of different tasks, we suspect that the neural networks, either be it attention networks or piecewise linear multi-layer perceptron, they generally take on different features and focuses different parts on the input. And that's why tuning the input differently or tuning the input equivalently will eventually still give different results for verification. And that is our conjecture why there's such a difference in the performance or the robustness comparison in terms of in different tasks, in lane departure warning tasks and in vision tasks.
Thank you. So do we have any other questions from the audience? You seem to be very quiet. So, but yeah, I see someone pop up.
Brian, hi. So basically,
yes.
Correctly understood. So you're doing that before, not at runtime, this verification. You do it before deployment, right?
Excuse me, I didn't get it fully.
So you do this verification not at runtime, you do it before deployment, but
right, exactly. So before deployment.
Is there some idea to combine runtime monitoring techniques? I mean, I know there's some like this neuron activation pattern monitoring. It's not related to your approach, but it's more like an extension of the verification. Or...
Right, indeed. So neural activation pattern is definitely could be an effective method for runtime monitoring. But in that regard, we would have no signal or no hint from the ground truth. So we don't know exactly what a correct prediction is for that certain input at runtime. And what we can effectively do is only get some abstraction from the training phase and monitor the runtime activation pattern against this abstraction from the training phase. And eventually this question boils down to whether or not the abstraction from the training phase is refined or is correct enough or not. And that is indeed a very interesting research topic to work on still, as you point out. Yeah, thank you.
Okay, now just was I noticed there's some work, and just this in mind. I think that maybe just another approach.
Yes,
I'm used to doing it before.
Yeah, but do you think, is it possible, for example, you can, I mean, if you do a lot of verification in terms of the ODD, right? So you can probably store some information in the memory and using this type of information as, for example, a runtime monitor. I mean, it's probably different with the activation pattern, but it's more like you store some verification results. Do you think that's possible, or it's difficult?
Question for me?
No, I'm asking Brian, because I mean, you mentioned runtime monitor, and activation pattern might not be easy, but I guess, I mean, some sort of summarization of verification results could also replace the activation pattern and so on. And that could probably be used as a runtime monitor.
So to be honest, I haven't thought about this question especially before, but I do. So in general, this approach, I believe is effective. So as this approach has been having an abstraction built from training phase or from verification phase, and move it to runtime and monitor the neural network during runtime against this abstraction. But I have, so I'm not sure what kind of abstraction we can build very effectively or very correctly on top of our ODD for our neural network, that we can really effectively and successfully monitor the neural network at runtime. And so, yeah, neural network activation pattern was one candidate that we tried before, and we do see some good result there, but still there are still a lot of false negative or false positive both actually in runtime. So how we can fine-tune the abstraction is still very ongoing research topic, I think. I'm not sure if that exactly answers your question, Professor Xiaowei.
Yes, thank you. I think yes. I mean, there's a large gap between, I mean,
yes, still
runtime monitor, and yes, that's it's still, I think it's still very active areas. That's a lot of proposals is coming basically every year. Yeah. But
okay, so I just thought of, if we have a couple of minutes more, I just thought of one more hint that we can extract from the training or verification phase into monitoring phase, is that we can at verification phase we can also record in our memory what portion or what parts of the ODD would there be more input. So what, in terms of like probabilistically, with a probabilistic fashion, we can record the data input and focus on those areas more, and monitor our neural networks on those very areas more refined, with a more refined fashion, such that we can eventually reduce the effort of average case analysis in runtime.
Yeah. Okay. I see people are start to leaving. So probably we should wrap up. Let's thank Brian for a great talk today. and hopefully we will see you in 2 weeks' time.
Thank you very much.